In this video, we're going to look at a series of graphs with the given function, and we want to identify the domain, the range, and all of the asymptotes. All right, so starting with this first one, f of x equals x plus 3 over x minus 1. Now, we don't even need the graph to answer the question about domain and range because of what we know already about graphing rational functions. But since they have the picture here for us, it looks like our domain is going to be everything except for what? Well, it looks like it's everything except for positive 1. We can see that vertical asymptote clearly marked there. And if we look at the function itself, we see that, yeah, there's going to be an issue here for x minus 1. So that means it's everything from negative infinity up to 1, union 1 to infinity. Or, as we've talked about before, you could also say that this is the set of all x such that x does not equal 1. You just have to make sure that when you're doing the homework that you are reading correctly about how they want your answer formatted. Okay. Now, what about the range? It looks like the horizontal asymptote is pretty easy to identify. It does not look like our function is crossing that at any point. So it looks like our range is everything except for 1. So almost like a copy and paste of the domain. That's just a coincidence. It's not an always thing. Now we need to identify our horizontal and vertical asymptotes. So let's start with the vertical asymptote, which we can clearly see is at x equals 1. Again, remember, for asymptotes, you must give the equation of the line. You can't just say it's 1. Okay, it's an easy way to lose points. Whether it's with me or in MyMathLab, you have to give it correctly. And your horizontal asymptote is also, or similarly, y equals 1. Now for the horizontal asymptote, let me go ahead and connect back to the video that we just did. You'll notice that these are your leading terms right there, x over x. So it doesn't really matter about the plus 3 and the minus 1 at a certain point. X over x reduces to 1, which means that's your horizontal asymptote. So cool beans. All right, let's see what's next. Okay, here's this one. Graph looks a little bit messier, but I think we can still do a good job of identifying everything. So my domain let's do set builder notation first. It's the set of all x such that x does not equal. Let's see, what can it not equal? Well, it looks like we're having an issue right here and then right here. And that first one is happening when x equals negative 3. So x cannot equal negative 3. And x cannot equal, looks like it's positive 1. Now, if we needed to verify that algebraically, we could just take this denominator and set it equal to 0 to see how's that affecting my domain. So alternatively, we can use that interval notation. So negative infinity to negative 3 union negative 3 to 1 union 1 to infinity. Again, both of these expressions are going to mean the same thing, the same set of numbers. Now my range. You'll notice here that for my range, I do have that horizontal asymptote, and I see that as I go out to the left and to the right, I'm not going to ever be equal to that. But do keep in mind that your range is for the whole picture, for the whole function. And if we take a look at what's happening right here in the middle, this guy's going all the way up, and he goes all the way down. So because of that, your range will be all real numbers. Even though we don't get to include 0 on the edges, it doesn't really matter. It's about what happens in the totality of the graph, which means everything from negative infinity up to positive infinity. All right, now our asymptotes. Okay, so I think we already identified that horizontal asymptote as being y equals 0. Right? And again, we can confirm that from the knowledge that we have when you compare those leading terms. x over x squared, the denominator has a larger degree, so he's going to 1 out. He's going to make things as small as possible, going to 0. All right, now we need to talk about the vertical asymptotes. So we see that we have 2. Again, that's going to correspond to the issues that we have with the domain. So that's x equals -3 and x equals +1. Again, we can see that in the picture. So hopefully no questions about that. And let's look at this last example. X squared minus 4 over x plus 1. All right, so our domain. Well, we clearly see a vertical asymptote, so we know we have to remove something from that, from the domain of all real numbers. So we got to remove the -1. So that's -infinity to -1, union -1 to infinity. My range is going to be very similar to what we saw in the last example, because you'll notice here that this piece here on the left goes all the way from -infinity up to +infinity. So it doesn't even really matter what the rest of the graph does. If one piece uses all real numbers, then that's going to be the range for the whole function. So the range is all real numbers. My vertical asymptote, we can see that in the picture. We can also see it from right here, from that denominator. What makes that denominator equal to 0? Well, that's when x equals -1. So it matches with the picture. Now, for the horizontal asymptote, we see that we don't have one, but we do have an oblique asymptote. All right, so we got to really focus in on here and try to see what this is. So we know that it's going to be y equals something. It's got a positive slope. And if we try to identify some of these points, right, it looks like we have a point here and here, which makes me think that that's a slope of 1, up 1 over 1. Now, to verify this, keep doing that same slope movement and see if you stay on the dashed line. So up 1 over 1, up 1 over 1, and so on. So yeah, I feel pretty good about that, that's going to be 1x. But what about that y-intercept for the oblique asymptote? We see that we are intersecting right here at 0, -1. So it's going to be y equals x minus 1. Now, again, that's me picking it off from the picture, but you can always do the math to confirm it, especially if you've got the function here. So with that x squared minus 4 over x plus 1, let's do the division, and let's see what we get. So I'm going to do the synthetic division because it's faster, and because I'm dividing by a nice linear factor, x plus 1. So -1 goes out here. I have 1x squared, 0x, and -4 for the constant. So remember how we label these guys. That way you know what is the value for each column. All right, so first things first, we bring down the 1. And then it's all about multiplication and addition. -1 times 1 is -1. Combines give me -1. Multiply times -1 is +1. And these guys give me a -3. So from this division, we see that we have x minus 1 minus 3 over the divisor x plus 1, which says that as x gets really large, my function starts to behave just like this. Or, I guess it really is the exact same thing, with the focus being right here on that, the x minus 1. Because this -3 over x plus 1, he's going to go to 0 as x approaches positive or negative infinity. So that means we're left with just x minus 1. So again, we picked it up from the picture, but we also did the math to verify.